Hello, this is homework help for a few problems on your test 3 for Calc 1. The first problem I got was question number 6. It says use the graph to identify the points on the interval AB at which local and absolute extrema values occur. And this is a conceptual problem for you to start understanding and continue to understand what local max and mins versus absolute extrema are, what they mean. And so our interval, we're focusing on right here at the x values of A to B, and we are looking at your local max and min and your absolute max and min. Now, your local max and min, you've got to have decreasing and then increasing for a local minimum, and then you've got to have an increasing function and then a decreasing function for a local maximum. So the first problem is asking about list the x values of the points where local mins occur. So we are going to be looking at the x values. So we're talking about local minimum points. And so here is a local minimum, and here is a local minimum. And again, we're only talking about the x values where that occur. So the x values where those occur are at Q and at S. So our x values are x equal Q and x equals S. And those are our local minimums because we have decreasing and then we go to increasing, decreasing, and then we go to increasing. We'll talk about what this B value right here means in just a second. Okay, the next is our local maximums, and our local maximums occur here and here, and that is because we are increasing and then decreasing, increasing and then decreasing, and that occurs at x equals r and at x equals t. Okay? Our next question is asking about absolute minimum, and so that's going to be our lowest value on the interval. And so it includes our endpoints, and this point right here is going to be our absolute minimum because it is the lowest value on our interval, and that occurs at x equals b. Then we have an absolute maximum, and that occurs at another endpoint, and that's our highest value, and that is when our x value is a. Okay? And so that is some graphical representation of what we are doing with our absolute max and min and our local max and min. Okay? Now we're going to look at number 13. And here, number 13. Determine the location and value of the absolute extreme values of f on the given interval if they exist. So what we have to do is we have to take this function right here, -5 cosecant x, and we are looking at this specific interval, pi over 4 to 3 pi over 4. Okay, and on that specific interval, we are looking for our absolute max and our absolute min. Now, it's not a bad idea to take a look at Desmos. Here's Desmos right here. So let's take a look at Desmos. And our function is -5 cosecant of x. Okay. And so here's here's where we're going to be looking. And I'm going to go ahead and put pi over 4. Where's my pi? There's pi. So I'm going to put pi over 4, and then I'm going to put 3 pi over 4 because that's going to show us our intervals that we're looking at. So I've got 3 pi over 4. Okay, and I need to get rid of that negative sign because we don't need that negative sign right there. And then we're not looking at any of these right here. So let's take those away. So what we do have just visually is this is the interval that we're looking at between pi over 4 and 3 pi over 4. And so when you're looking at the graph, you can kind of get an idea of what we're doing. Now, and you can see right there, we are going to have a critical value inside this interval. So we're going to have to solve that algebraically. But here, you're going to be able to see at pi over 4, let's try to get that to, there we go, pi over 4, and then we've got another value right there at pi over 2. So this is what we're looking at. So we can see that pi over 4 and 3 pi over 4, those are going to be our absolute minimums because that occurs at the end of our endpoints. And then pi over 2 is going to be our absolute maximum because that's going to occur at a critical value. Now, this is the visual representation of what's happening. We need to also be able to do this using calculus and looking at the derivatives. So this is where we're going with this, but let's talk about how to do this using calculus. Okay, so let's go back. Here we are. Okay, determine the location and value of the absolute extreme values of f on the given interval. Okay, so I went ahead and pulled my unit circle in here because we're going to have to use our unit circle. So the first thing that we're going to do is we're going to start with our function. And so my function is f of x equals -5 cosecant of x. Okay, now, just a little reminder, cosecant of x is the same thing as 1 over sine of x. Okay, so you've got to be sure that you have some understanding of trig. That's going to come into play here. Now, we're going to find our derivative f prime. Okay, you don't have to have your trig derivatives memorized, but you are going to have to be able to pull them in. So I'm going to have my -5 times, and that's just going to be the derivative of cosecant of x. You don't have to have it memorized, but you will have to be able to use it based on the list that you're given. So the derivative of cosecant of x is negative cosecant of x times cotangent of x. Okay, and so then when we multiply that, we have f prime of x equals +5 cosecant x cotangent x. Okay, then we are going to set our derivative equal to 0, and we're going to solve. And so you got to think back to some Math 112 and some Math 113 here. Okay, we've set the derivative equal to 0. This is a factor. Okay, so 5 is a factor, but we know 5 is not equal to 0. So I'm going to set cosecant of x equal to 0, and I'm going to set cotangent of x equal to 0. So I've got cosecant of x equal to 0, and I've got cotangent of x equal to 0. Okay, now, cosecant of x, that is 1 over sine of x. Okay, now, when sine of x is 0, so that's going to be at 0 and at pi, or at 2 pi, so 0, pi, and 2 pi, okay, that's when sine of x is going to be 0, but I can't have 1 over 0. So for a rational or a fraction to be equal to 0, our numerator has to be 0, and that doesn't happen. So there is not going to be a critical value from this, okay, because there is no value where cosecant of x is equal to 0. Okay, now cotangent of x, we have to think about our numerator. Remember that cotangent is cosine of x over sine of x. Now we have to make sure that this is not undefined. So we know that sine of x can't be 0. Okay, and sine of x is 0 at 0 and at pi. Okay, so we know it's not going to be 0 or pi. But we can look and see where cosine of x is 0, because our numerator's got to be 0. And cosine of x is 0 at x equals pi over 2. and x equals 3 pi over 2. Now, 3 pi over 2 is not going to be in our interval. If you remember, looking back to our original problem, the interval that we are dealing with is pi over 4 to 3 pi over 4. Okay? That's the interval that we're dealing with, and this point right here is not going to be in that interval. Okay, so we now have our only critical value that we're working with inside this interval, and that's pi over 2, and then we're looking at pi over 4 and 3 pi over 4. So we are going to go back to our original function and plug these in. So I'm going to have f of pi over 4. The reason that we're doing pi over 4 is that it is an endpoint. Then we are going to have f of pi over 2 because that's a critical value that we found. And then we're going to have f of 3 pi over 4 because that is an endpoint. Okay, so we have to do our endpoints for our interval because we're looking for our absolute extrema. Okay, so that's what we're doing here, endpoints. And then here we've got our critical value, and we found our critical value. And this critical value is not in our interval. Okay, so now what I'm going to do is I'm going to plug in pi over 4 to my original. So that's going to be negative 5 times the cosecant of x. Oh, I'm sorry, we're not going to plug x in. We're going to have pi over 4. Okay, now that is negative 5 over sine of pi over 4. Okay, and sine of pi over 4 is square root of 2 over 2. So negative 5 over square root of 2 over 2. And when you do the algebra for that, you end up with negative 5 on the square root of 2. Okay, then here we've got negative 5 cosecant of pi over 2. Okay, so that's going to be negative 5 over the sine of pi over 2, and the sine of pi over 2 is 1. So that's going to be negative 5 over 1. So that's going to be negative 5. Then we are going to find negative 5 cosecant of 3 pi over 4. So it's going to be negative 5 over sine of 3 pi over 4. And sine of 3 pi over 4 is right here, and that is also positive 2, or positive square root of 2 over 2. So that will be negative 5 over square root of 2 over 2. And when we simplify that, we get negative 5 on the square root of 2. So what we have is this is our absolute minimums, and this is our absolute maximum. So let's write that out. So we are going to have absolute minimum Okay, our absolute minimum is negative 5 on the square root of 2 and occurs at pi over 4 and 3 pi over 4. Okay, and then our absolute maximum is negative 5 and occurs at pi over 2. Okay, There you go. And that is number 13 from our practice. Number 13 from our practice test. And all of these are version 1. I do all the version 1 so that you can see version 1. And then you can go back and you can look at version 2. So all of these are from the version 1. And version 2 is similar. It's just a different set of numbers. Okay? Now, the last one that I'm going to do is number 36. 36. Number 36. Here we go. A rectangular tank with a square base. Rectangular tank with a square base. And an open top. And it has a volume of 108 feet cubed. Okay, so then we are going to construct that out of sheet steel. And we want to find the dimensions of the tank that has a minimum surface area. A minimum surface area. So let's kind of think about, so our rectangular base is going to have a bottom to it, and it's telling us that the bottom of this is a square. So that means this length and this length are exactly the same. Okay, that's what that means. Then our rectangle is going to have a height to it. And so I'm not a great artist, but let me see if I can draw a cube, or not a cube, but a rectangular. Okay, so here we've got, and then so our rectangular down here at the bottom is a square. Okay, and then we're going to go all the way up. But this part, the very, very top, is open, and that's going to be important when we figure out our surface area, because we're not going to have a top. So we're going to have a square at the bottom, but we're not going to have a square at the top. If you think back to our cylinder problem that we did in class, where we had a circle at the bottom and a circle at the top, this one, we're not going to have a circle at the top, or we're not going to have a square at the top. We're only going to have the bottom one. So when we think about the surface area, typically you would have 2 times your S times S. Okay, so that's surface area. So this would represent the bottom, and this would also represent the top. Okay, so typically that's what you would have. Now this does not have a top. It's an open top. So we're going to remove that top from it. Okay, then we would have 2 of the sides right here. So you'd have this side, the area of this side, which is going to be S, because that's all of these sides right here are the same. So this is going to be S times our height. Okay. And then we're going to have another rectangle, this rectangle right here, and then the rectangle on the bottom is also going to be 2S times height. And the reason that these are exactly the same is because this is square. If this wasn't square, then they wouldn't be the same. But because it's square, it is. Okay, now, so this would be your surface area if all of these sides were solid. But because we don't have a top and we know that the square is where the base is, we're going to come back right here and we're only going to have that times 1. Because we only have one bottom. We don't have a bottom and a top because of the way that the base is created. Or not the base, but the rectangular tank is created. And you can think about a fish tank. You know, a fish tank has, 5 sides. It doesn't have a glass on the top. So think about a fish tank. And this is a fish tank where the bottom of it is square and then it's some height. Okay, so this is our expression that we are going to use for the surface area. This is the expression for the surface area. Now we're going to go back and we're going to fill some different things in. Now, let's talk about this right here, okay? This is the volume, a rectangular tank with a square base, an open top, and a volume of 108 feet cubed. So that's going to be V equals S times S. So usually it's length times width times height, but we are representing that square as side times side, and we're going to represent that with an S. So that's going to be side squared times my height. Now we know my volume is 108, so it's going to be 108 equals side squared times H, and so H can be represented by 108 over S squared. And so everywhere we've got an H, we're going to put S squared. Now something that I could do before I get any further is I could add these two together. And the reason I can do that, again, is this square base. If the base wasn't square, we'd have to keep these separate. But 2S times H plus 2S times H, I can go ahead and do that. So I'm going to have the surface area is side squared plus 4SH. Okay, and we know that H represents or is 108 over S squared. So I'm going to have SA equals S squared plus 4S times my height, which is 108 over S squared. Okay, so now I'm going to have surface area equals S squared. I am going to multiply 108 times 4, and that's going to give me, 512. Okay, 512. Okay, then I've got S and S squared cancel, so that's an S in the denominator, and I'm going to rewrite that as S to the negative 1. And it wants us to use A, so SA and A mean the same thing here. I'm just going back to this where it says that it wants us to use A. Okay, so I've got A equals side squared plus 512 S to the negative 1. Okay, so that is my function, S squared plus 512 S to the negative 1. Okay, now the interval of interest that we're going to do, we have to start at 0 and we can go to infinity. Okay, so our height really could be anything. Okay, as long as it's positive. Okay, now I'm going to need to go to the next slide so that we can write some of this out. So we've got our function. So I've got A equals L squared, or S squared, I'm sorry. When I was working this out, I used L. So let's do S squared plus 512 S to the negative 1. Okay, so now we're going to take the derivative of that. So I have A prime equals 2S minus 512 S to the negative 2. So I am going to go ahead and set that equal to 0, and then I'm going to have 2S, and I'm going to rewrite that as 512 S squared in the denominator. Okay, so 512 over S squared. I am going to move this over to the other side by adding that to both sides. So I have 512 over S squared equals 2S, and I will end up with 2S cubed equals 512. Go ahead and divide both sides by 2, and I get S cubed equals 216. Then when I take the cubed root of that, I have S equals 6. Okay, now that is my side of my base. So my square base is going to be a 6 by 6. Okay, so this is the side of square base. Okay, now to find my height is 108 divided by 6 squared. So that is going to give me a height of 3. And we are talking about feet. Okay, so this is going to be 3 feet. This is going to be 6 feet. Now, it's important that we make sure this is a minimum and not a maximum. So this is a rectangular tank with a square base, and we want to find the dimensions of the tank that has the minimum surface area. So that means that we're going to use the least amount of glass. That's why this is important. Now, to find the minimum, we're going to go back to our derivative, and we're talking about using this 6 as a critical value. So we are going to have intervals 0 to 6, and then we're going to have 6 to infinity. We want to make sure this is a minimum. So then we are going to use the derivative. We're going to plug a test value into our derivative to make sure. Now, this is the first derivative test, so we're going to make sure that this works. Okay, so when I plug 5 into my derivative, okay, so here's my derivative right here. When I plug 5 into my derivative, I get a negative value. Okay, so that means my function is decreasing. Okay, then when I plug 7 into my derivative, okay, when I plug 7 into my derivative right here, I get a positive value, and that means my function is increasing. Okay, so what this means when I have a negative value and then I have a positive value, using the first derivative test, that means that 6 is where the minimum occurs. Okay, so s equals 6 is the minimum. And if we plugged that in, is the value where minimum occurs. Okay? So this is the first derivative test to make sure that at s equals 6 that we have a minimum surface area. Let's see what the rest of the question asks. It just says the tank with the minimum surface area has a height of 3. Okay. And a square base with each side being 6 feet. Okay. And so that's the end of your problem.